Hello, everybody, and welcome to the National Association of Regulatory Utility Commissioners webinar series on the Water and Thermoelectric Energy Nexus. We have partnered with Sandia National Labs to present this webinar series to you, and this is the fourth of four, and we're very excited to capstone this program with you. I would like to introduce at this time Vice-Chairman Jack Betkoski from Connecticut. He is on the regulatory board there for the Public Utilities Regulatory Authority, and he's also our most recent past president. So we are very happy to have Chairman Betkoski. Thank you.
Thank you so much, Carrie. I appreciate the introduction, and I am actually the immediate past president of the National Association of Regulatory Commissioners, and I'm really excited about the topic today because my theme as president was Power Together, the Water Energy Nexus. The whole idea behind that was to really raise the awareness of water and energy issues and how they go hand in hand. And every time we did any type of speeches or presentations throughout my 15 months in office as president, we incorporated the whole water energy nexus. So I'm really excited to be part of the capping of this four-part series on water energy and the importance of it. We always look upon water at times as the stepchild in utilities until you don't have it, or if you're fighting over it because of jurisdictional types of things. So we're very, very excited today to have with us to give a presentation, and then we're going to have a response. Vincent Tidwell, who is with our partner from the Sandia National Laboratories, who's going to give a presentation on some of the works and articles that he's done on this subject. And then we're going to hear some response from Kate Coughlin from the Lawrence Berkeley National Laboratory, and from Peter Keegan, who is a chief engineer with American Water Company, which is one of the largest water company in the United States, largest regulated water company in the United States. So without further ado, we'll start with Mr. Tidwell. Good afternoon, sir.
Thank you, Chairman Betkoski. I appreciate you introducing this. So for those who've been on the other webinars, we're going to kind of shift gears a little bit. And whereas we've been looking at the issue of looking at water issues as they pertain to electric power generation, we're going to kind of flip the coin over and begin looking at energy for water production. So do we have the slides yet? I do want to recognize my co-author, Barbara Moreland. She's at Portland State University, used to be at Sandia. Went back to get an advanced degree, and also want to recognize the Department of Energy, Office of Electricity that supported this work. Next slide. So the basic takeaways that I hope you get from this presentation today are as follows. The water sector accounts for a pretty significant part of our electricity consumption in the U.S., somewhere around 4 to 8%. It could be even higher if you add in end use. We'll talk a little bit more about that in a moment. We're also concerned because this demand's likely to grow because of changing populations, changing water sources, and changes in water treatment technologies. We'll also see that electricity use for water is highly locationally and sectorally dependent. So it's very heterogeneous across the U.S., really is very dependent on where you're at. The growth, there's a lot of variability in what the growth could look like over the next 20 to 25 years, or 20 years. That should be 2035. We're over the 2015 levels, but 1 to 18%, somewhere in there, depending on how things evolve over the future. And there could be very significant change within the sectors, as we'll talk about. And then why should this be of any use to energy planners and regulators? Well, I think you need to understand your basic makeup of load and how that load could be changing in the future. And since the water sector is one of the larger single sectors of electricity use in the United States, that becomes pretty important. So next slide. So what is the issue? Energy for water. Well, we use energy in the water sector in a lot of different ways, for pumping and pressurizing water for irrigation. We use it to pump and move water for large-scale conveyance, so these large basin water transfers. As you see, the Central Arizona project there in the top right, our wastewater collection and treatment, as well as drinking water, the treatment and distribution of this water. As I've already mentioned, the water sector, just to deliver the water, consumes 4 to 8%, possibly a little more than that, of total energy consumption. If we add in end use, so things like our hot water heaters and dishwashers and whatnot, we can kick that up. Almost 13% of all energy is consumed there. Today, we're just going to look at the amount of energy to deliver water in these major sectors, to deliver and treat the water. Next slide. And as I've already mentioned, the demand for energy in the water sector could grow, and for a variety of different reasons. As you see kind of right there in the middle, conventional water treatment's fairly low, but future technologies, we're using more brackish water, we're using more seawater. These all require a lot more energy, at least with the technologies that we have today. And you can see there on the far left that our our reuse of wastewater and use of desalination water is growing, and is growing pretty quickly. We also know that there's more and more concern about a variety of contaminants, particularly trace contaminants in our water, and so pharmaceuticals and other types of chemicals, and so treatment for those could require a lot more energy. We also are still having plans to build additional conveyance projects to move water across mountains and to different various transboundary projects. So there's a variety of reasons why water or energy in the water sector could go up. Next slide. So for these reasons, our objective here has been to map out the electricity. So I say energy, but I really mean electricity. We're focusing on electricity use for water services, and we're doing this at the county level. And we want to distinguish between these key different sectors and how differently that energy use may look. So for large-scale conveyance, moving water, transboundary water projects, irrigation, drinking water, and wastewater. So we're going to map each of those out individually at a county level across the entire United States. We're also concerned about, well, what's it going to look like going into the future 20 years? So we're mapping out kind of the current use in 2015 is kind of the baseline data that we have, and then we're looking out to 2035 and considering how population change, changes in groundwater levels, changes in water sources, in water treatment, how these could impact our water use and where across the United States. Next slide. So what I'll do now is kind of step through all 4 of these key sectors and talk about how we made these calculations, and then show you what kind of the 2015 numbers are, and then what the projected future might look like for each of these. So first, we're talking about the large-scale conveyance, again, moving water between basins, in many cases over mountains, particularly in the West. So the basic cost to energy is the water to lift, or the amount of energy to lift the water, the difference between, well, it's really not even just between the source and, well, any lift that you have to do between the source and the destination. And so you can see the simple equation there in the middle. Basically, we need to know how much water we're moving, how high we have to lift it, and then the efficiency of the pump, which is the alpha there on the bottom of the equation. So basically what we're able to do using GIS, we're able to know the different types of reservoirs, what they're used for, and we can map out, you know, the pipelines, and we from there we also have ideas. We have knowledge about the different reservoirs and what they're used for, and who's using those reservoirs from the Corps of Engineers and Bureau of Reclamation. And so we can put this information together and get a good idea about the values in our equation here, and we're able to calculate at least, you know, at a rough level in a consistent way across the whole U.S. where this energy might be used in for large-scale conveyance. We also are looking forward and thinking about where new projects may be built. And so there's been a variety of different sources like the Western Resource Advocates and others who have compiled lists of different areas that are considering construction of such projects. And so we've used those. We've also done some of our own web searches to try and identify where those may be occurring. Next slide. So this next slide shows a map of the U.S. for our projected electricity use for large-scale conveyance. The color scale wide is 0, and you know, as the colors get warmer, the energy use increases. You can see it's on a county level. Megawatt hours per year. This is consistent across all the different maps that you'll be seeing. Here you can see that the largest use is in California. Almost 84% of all the water use in this, or energy use in this sector, is in California, mainly through the Central Valley projects and related projects. And then the cap in Arizona would be the other, the Central Arizona project would be the other major project. But you can see there's other smaller projects scattered out across the West. Overall, currently it uses about 5% of all the water sector electricity use. Next slide. So this next slide shows where we're projecting future projects based on various projects that are either under construction or that are being planned. Again, you can see these are largely in the West, mainly in Colorado and New Mexico right now. About a 15% increase is projected based on what we've been able to find. There have been a lot of other projects talked about, but many of those either have been put on indefinite delay or are not being considered anymore. But these were the ones we've been able to find. You can see that there are large-scale conveyance projects in the East, but for best that we could tell, all of those were largely driven by gravity feed, so didn't require pumping. So folks have knowledge of projects out East. I'd certainly be open to those and learning about them. Next slide. So that was large-scale conveyance. Now we're turning our attention to irrigation. Again, for irrigation, where is the electricity used? Well, it's to pump and pressurize water for irrigation. Again, using the same basic equation through the USGS, their water use data website, we're able to, at a county level, to be able to determine water withdrawals or pumping for irrigation, as well as depth to groundwater. From the USDA, we can determine the amount of back pressure that they're using, as well as the type of pump. So we're able to distinguish electric-powered pumps from diesel and other types. And so that's used to be able to map energy use across the U.S. for irrigation. Then going forward in time, we consider changes in groundwater levels. Here we're using the GRACE data, the satellite data, so it's very large scale, so kind of the average for the basin. This is work from Framaghetti and Rodell in 2013. Basically, we're taking the historical past 20 years and just projecting them forward. That's about the best we have to work with this time, but gives us an idea of what that could look like, probably under worst case. We're also considering there's been some pretty big changes over the last 20 years in terms of withdrawals, and you can see in this map kind of here in the middle, the 20-year change in irrigation, we see movement reductions in withdrawals in the western U.S., while we're seeing some sharp increases in the eastern United States. So we're taking that into consideration looking forward. Next slide. So this next slide shows energy use, electricity use for groundwater that's used for irrigation. You can see that's largely focused in the western United States, but there's some significant irrigation still in Florida, as well as very significant irrigation along the lower Mississippi. You can also see the Ogallala aquifer, that High Plains aquifer, that they're in kind of Texas, Nebraska, Kansas area, Central Valley of California, and others in the western United States. The next slide. This is for surface water, so largely pumping out of a river or lake and then pressurizing that water for irrigation. Again, you can see largely focused in the west. Overall, you put these two together, surface and groundwater together, obviously California, Idaho, Texas, Arkansas are some of the leading states where water is used this way. 29% of all the water sector electricity use goes to pumping for irrigation. Next slide. So then projecting forward, what might things look like 20 years from now? And again, the real main driver of change here is in potential changes in irrigated agriculture. And so there's been a big shift over the past 20 years from surface to groundwater in California, but otherwise, and somewhat so in Nevada and Oregon, but for the most part, the rest of the West, you see slight decline in irrigated acreage, and thus would an accompanying change in the overall electricity use. Out east, you see growth. It kind of depends on which state you're in. If we go to the next slide, you can see the same thing for surface water. Here you can really see all across the West a potential decline in energy use because of if we continue on these same trends of declining irrigation in the West. So you see increase in places like Nevada or North Carolina and Kentucky in the east, while big declines in Montana, Colorado, Wyoming. Overall, again, you can see up to a 50% decrease if these kinds of trends continue. So that would be kind of a best case in terms of energy use, but whereas, probably little or no change would be kind of the other end of the spectrum. Next slide. So now we're talking drinking water and energy use there. Here we lean heavily on a report by EPRI where they looked at the various unit processes in your normal drinking water facility, and then as that data is not broadly available, they were able to roll it up into different kinds of systems, as you can see in this top right little table, in terms of public supply, domestic versus self-supplied industry, and where the source of water was from. So we use these basic factors, and then use the amount of water that the municipal sector or public, domestic, or self-supplied is using. We get that data from the USGS. We're also able to complement that with the amount of energy to lift the water if they're using groundwater and the depth to groundwater, again using USGS data. So in this way, we're able to get a county level measure of energy use, albeit kind of rough, but still gives us a consistent way of characterizing that. Then looking forward in time, we have ideas about how the population may be changing based on data from the Census Bureau. Then we also couple that with changes in groundwater levels, again, like we did for irrigation, same data set, and then changing water sources, which could be very, very important. Here we have a variety of reports which project future where new desalination plants are being planned or likely or under construction all across the U.S., both brackish and seawater plants. We have data right there in the middle. You can see the Bluefield research, again, kind of a rough idea about how wastewater reuse might look in the future, where new capacity is likely to be added and in which states. And so we use that and distributed it based on growing population and where the new water demands are likely to be realized. Next slide. So the next slide shows kind of the baseline in 2015. This is for groundwater systems, and so you can see pretty evenly distributed all over the U.S. You can also see a lot of the major cities, metropolitan areas really pop out all around. Chicago, they're in the Miami, Houston, other areas all across the U.S. Next slide. A little more sparse for the surface water-based systems, but again, still driven largely by large municipal areas. California, Texas, Florida, and Louisiana across, both surface and groundwater are the largest, have the largest electricity burden for the drinking water system. About 37% of all the water sector electricity use is in the drinking water sector. Next slide. So this next slide gives you an idea about how changes may occur. You can see this light blue is where energy use could be going down because of lower populations primarily, and other changes in the systems. Texas, Colorado, California, Georgia are expected, at least according to this data, could see the largest growth, largely because of large growing demands for large population growth, along with plans to build substantial desalination capacity. A projected overall about a 19% increase over the next 20 years nationwide. Next slide. And then finally, we get to wastewater. Here again, we rely on the EPRI report from 2013, where basically they again characterize various unit processes, and then so we can use their data, their factors for different levels of treatment. You can see there in the top right. And so we know what kinds of plants, how much water they're treating, and at what level of treatment from the clean watersheds needs survey down below from EPA. So we're able to get that data and calculate kind of what the 2015 energy use in the wastewater sector is at again a high level, but it gives us a consistent measure of what that energy could look like. And then to project in the future, again, we're looking at changing populations. We considered increasing treatment levels overall, going to at least secondary water treatment across the U.S., and then considering the offsetting effect of biogas utilization. And so we have a U.S. DOE database that helps us know where those plants are and where the most likely expansion to use biogas will be. Next slide. And then so here's the map for 2015 wastewater use. Again, pretty consistent all across the U.S., some level of use. Again, greatest use tend to be in large municipal or metropolitan areas. Some of the largest use here, different than what we've seen before, are tend to be in the East, New York, Ohio, Texas, Michigan. Again, about 17% of all the water sector electricity use is in the wastewater sector. Next slide gives us an idea of how things may change. And you can see here a lot of decrease. In fact, overall, US-wide, we're looking at maybe up to a 37% decrease, part because of changing populations and the utilization of biogas much more extensively. So we can see certain states like Colorado or Georgia could increase, while places like Nevada, California, and Arizona could be decreasing, again, because of much more broadly used biogas to offset their energy use in this sector. Next slide. So I believe this next slide is the totals for the 2015. So here we've added up all 4 sectors, groundwater, surface water together and into one map. And of course, you know, the scales changed considerably here, but you get an idea. You can see the importance of irrigation, you know, making the West overall a little higher than what we see in the East. But then again, you can see a lot of the energy use clustered around large municipal areas representing our drinking and wastewater energy use. And so states like California, Idaho, Texas, and Arizona are at the top of the energy use. In fact, if you click one time, you can get us advance one more time. I think, there we go. So you can just see here how precipitous that, you know, California, Idaho, Texas, and mainly those 3, very significant energy use compared to all the other states. This is just in terms of total electricity use across all the different sectors. So there are some big differences by state. Next slide shows the overall projected change, and you can see there's big winners and big losers. We're still working on this, and we'll be dividing into a high and low case. We're not quite there yet here, but gives you an idea of if we put all the major changes together. You can see in some states a potential for significant declines in overall energy use, largely because of shifts in potential irrigation practices. Whereas, you know, in other places, particularly around large municipal areas, you still have the chance for growth due to your drinking water and, in some cases, your wastewater sector. So overall, either between a 1 to 18% kind of a low and high case, roughly, that one could expect overall national change. But again, if you remember from each of the sectors, some, you know, could see substantial increases like drinking water, whereas others like irrigation, and again, the irrigation depends on whether you're in the East or West, you could see some big changes there. So it's very important to keep an idea about which sectors are changing, because that has a big influence on spatially where you're going to see those kinds of changes. But the largest increases are likely in California, Texas, Arkansas, and Georgia, at least according to these preliminary results. So next slide. I think that is it. So it gives you an idea again. The water sector is a very important part of our overall energy consumption, 4 to 8%. It's one of the largest energy using sectors in the United States. This demand could grow due to population, water sources, and water treatment. It's highly locationally and sectorally dependent. There's a whole range of what the future could look like depending on changes in irrigation practices, population, where we're getting our water from, how we're treating, and to what extent we're capturing energy in our wastewater. And so hopefully this kind of information would be useful to the energy planners and regulators to kind of better understand, or at least be aware that the loads from the water sector could be changing, and for what reasons. So with that, I will turn it back over to Chairman Betkoski and let you take it from there. Thank you.
Thank you very much, Vincent. Excellent presentation. I'm always astonished when I hear about some of the percentages and statistics when it comes to water usage in both the water and wastewater aspect of the utility around the United States. And people really do, I wish we could get this kind of information out more. And as I said at my introductory remarks, people don't realize how important water is until we don't have it. So very, very well done. Great, a lot of information there. So with that, I'm going to turn it over to our panelists to kind of react to the presentation, maybe give some additional comments. And we'll start with Katie, and maybe when you give some of your thoughts on this. We want to look at beyond the aspects of the planning, the water energy nexus, but what to you is important from a policy planning and analysis in your role?
Okay, thank you. Well, thank you for the opportunity to participate in this. And that was a very interesting presentation, and it's nice to see someone try to gather up this information at the national scale, because I know a lot of the water planning is done in a very local way. So just for a bit of background, I work with a team at LBL that does mostly energy efficiency policy and some renewables. But we also have a team that's been doing the policy impact analysis for the EPA WaterSense program, which is sort of their analog in the water sector for the Energy Star. And we're very interested in the problem of demand-side modeling for the water sector. I think I can make an analogy in Vince's presentation with water and wastewater treatment facilities. It's sort of like modeling energy demand, but using power plants as the kind of basic unit of demand. And so I'm interested in kind of going behind the power plant to see what's the driver on actual demand for water from the perspective of buildings and facilities and end users. And that's something that at LBL we've been trying to sort of figure out how to create models that would span like basically the entire country. That's similar to what we do for the energy sector. And I think it's interesting not only for the water industry, but also because I think in the water sector, there's a couple of things that are going to drive change in the future. One of them is there's a real concern about supply adequacy. I know it's probably mostly in the West, but even in regions where there are sort of abundant precipitation, there are increasing water quality problems and new contaminants emerging that are quite difficult to treat. So one of the ways of dealing with that is people are thinking more and more about moving to somewhat decentralized systems and doing a lot more reuse. So this has the potential to create new end uses essentially for energy, both at the building level or at the farm level or at sort of industrial facilities, either to reuse the water and which would involve treatment, or even to take kind of their groundwater supply or their surface water supply and apply some additional treatment to it before it's used in its application. Another thing about water supply is it's very closely tied to weather phenomena and hydrology and things like deep groundwater recharge, which are very difficult to predict and to assess. And so there's a lot more variability potentially in the water supply, which usually has to be made up with some kind of mechanical process, which would then use more energy. So I think there's a lot of value to kind of moving to a more end-use based analysis of water use and building that into these projection models so that we can understand, so for example, how you could modify both water use efficiency and water sort of changing the water resources that are used for supply and how that would interact with the energy sector. So more specifically to what Vince presented, one of the things I was struck by is the potential decrease in energy use for irrigation in California, because that seems a little counterintuitive to someone who lives here. And I was wondering, the biggest source of variability that I would think of for that is actual precipitation and water demand for irrigation and how that interacts with drought and rainy season. So I was wondering, Vince, if you were able, does the data allow you to do any kind of estimate of what that variability would be based on weather?
Unfortunately, the USGS data is only on 5-year increments. If we got into some of the state level data, we might be able to see some of that. I think a lot of what you're seeing across the West, it's kind of a mixed bag. Some of it is abandonment of farms that are largely being gobbled up by cities and the like. So, there's some small percentage of loss there. And then particularly on the withdrawal side, you're seeing improved efficiencies in irrigation. And that's, in part driven by regulation and or just the cost of moving the water around. And so I think you're seeing, a bit of both of those that are at least my perception would be the drivers for the changes that we're seeing there.
Okay. And then in your projections for the water utility, sort of water, energy for water, drinking water, and energy for wastewater treatment, did you consider any of these issues with emerging contaminants?
Yes, in a simple way that what we did is we just increased the wastewater treatment level. I think we moved everything to an advanced level and just assumed that all plants would have to, for one reason or another, improve their overall level of treatment to that level. I know that doesn't necessarily address the specific treatment requirements for those kinds of contaminants, but it was an effort to try and reflect those kinds of higher scrutiny on water treatment.
Mm-hmm. And I guess in your review of the available data, do you have a sort of any idea of what you would see as the most important gap to try to fill in the near term?
Well, I think there are many factors. I think part of it would be the big ticket items, if you will, would be things like changing irrigation practices. Those have a very significant impact on the overall complexion of energy use, and kind of digging deeper into that process and understanding both what's, the extent to which economics, technology, and just behavioral dynamics as well are all playing into that. I think that's a pretty right place for, and just better data overall. I know the USGS is working hard to improve a lot of their characterization, particularly of consumptive use, which will play into all of this. The other places would be better forecasting of where reuse of wastewater, desalination, as well as the biogas. The data that we had to work off of looking forward, was pretty spotty in places. So, and then as you mentioned, the whole kind of water use dynamics going forward in terms of how people change their water use practices in the home will have a huge change as well in terms of their water use, the overall water use, as well as wastewater production. So, those are other factors which, will all bear on these kinds of calculations. Mm-hmm. So there's a lot of places that we can improve. The hope here is it just gives us kind of a starting place to see across the U.S. in a consistent way what this water or energy for water use looks like, and how it could be changing and where.
Right. Okay. And my last question is, I'm wondering if you have any insight into whether there are kind of end uses that are well adapted for using renewables as opposed to kind of grid energy, and whether that could be used to kind of maybe help improve the sort of load factors for renewable energy sources.
Yeah, I know that there's, particularly in the wastewater side of things, I know that there's been pretty considerable ideas about trying to combine those. Similarly, you're combining some of these, and in fact, I guess I should put a plug in for the Department of Energy just Thursday, they put out a call for a clean water desalination hub, which is intended to put, I think, $100 million over the next 5 years into looking at advanced treatment technologies, and a key part of that would be looking at integrating renewables into both the water treatment side of things as well as the wastewater side of things. I know that is an important part of it, the combined heat as well from power plants and other processes in combining that with water treatment. And so, if we can bring the cost and the energy burden down from some of these, and then, as you mentioned, combining that with renewables, again, that could have a pretty significant influence on our energy use in the water sector.
Okay, thank you, Katie and Vince. And we're going to ask Peter a question from the regulated water utility perspective, and then he can react to Vince's presentation as well. One of the things here in the state of Connecticut that we've done is that we have developed a comprehensive water plan it's a 600-page plan for the entire state of Connecticut, and we had many people weigh in on it, stakeholders from the environmentalists to the utilities, regulated utilities, public sector, municipal companies, legislators, everybody get involved with it. But one of the things we always talk about is conservation. So I guess, Peter, as you react, I would ask that what are your areas as a company focus in for reducing your energy demands for drinking water and wastewater?
Yeah, it's a good good question and an important part of this. I think I was intrigued by I guess it was Katie said that historically water planning has been very local, and as Vince was showing his maps of the country, I found myself looking in very specific geographic areas that we were active in, and trying to understand the trends that Vince is seeing in those areas. And I can't say I saw anything that I disagreed with. I think exactly the trends that Vince is projecting are things we're seeing. And so on the drinking water, there were areas where Vince is projecting decreasing energy intensity for drinking water, and I think that's to the conservation efforts that have been ongoing for a couple decades now. With efficiency of in-house appliances and fixtures, really having a significant impact on per capita consumption of water, and so in many areas you see that that trend has been ongoing for like I said, a couple decades, and we're not really sure where the bottom of that trend line is. They've continued to decline in many places on a per capita usage. So that's been a great thing. That certainly helps the energy equation. The less water we have to pump, the less energy we use, and then the less energy we have to spend to treat it on the wastewater side. So that I think you see in many of these geographic areas that's a major factor. The other place that drinking water utilities, private and public both, have I know been focused for a number of years is on simply reducing leakage out in the distribution system, and on wastewater systems, reducing leakage into the wastewater systems, which again means that's water you have to pump and treat. So buried infrastructure is been identified by many agencies and many studies as being an ongoing challenge, requiring lots of ongoing investment, and it's a difficult area because even with new technologies that have helped, there's not a panacea out there of technology that makes it inexpensive to renew buried infrastructure. So I think you'll see, from an investment in the water and wastewater utility industry, it's going to continue to be a major driver of costs and expenditures in the industry to try and reduce the the amount of leakage that's happening, as I said, both out of distribution systems and into collection systems. But with that investment,
Peter, excuse me, could you give us a example of some of the technology that you have worked with to reduce water or wastewater?
Sure. Yeah. So on leakage out of water distribution systems, there's first the challenge of identifying the leak location, and so there's been some interesting technology advancements in recent years using satellite imagery and even drone technology to try and detect temperature differentials that might be indicative of a leak location, and even some that are looking at chemical differentials in near surface, I'll say groundwater, water table water that might be indicative of leaks. So that's an area that we're tracking closely and testing out to see if it can be used. So identifying the leaks is often the first hurdle, and then once we've identified it, the question is whether to do spot repairs or more extensive repairs, and that really is a function of the infrastructure that's in place in that area. In dense urban areas, it can be difficult to do full replacement, and so then we're looking at different slip lining technologies or structural liners that have been developed over the last several years that can make the challenge of replacing pipelines in dense urban areas or in other hard to get to places, or even over larger distances, it can make it more affordable. So those are a couple, and then those also apply to collection systems. There are liner technologies that can be inserted into existing gravity sewer lines. They require temporary pumping in many cases, and still some disruption in the process, but they can be more affordable than outright replacement of gravity sewer lines that tend to be deeper and maybe more difficult to get to.
I mean, fortunately, the larger private investor-owned water companies and those that have the capital capacity to put in good leakage systems is helping us. But the challenge we have, is, as you know, is that the smaller systems that have the leakage beyond the 15% acceptable by NARUC standards are the ones where we really have lots of challenges.
Right. Yep.
It's because I mean they just don't have the capital there. Many times with the smaller, and your company I know has taken over many of these smaller systems. It's a big challenge for us. Both regulated.
Yep. Yep. It absolutely is, and as you said, 50,000+ water systems in the United States, and all they all have the same challenges, or to different degrees, but that is a real major hurdle for many small ones. I was just going to comment to,
go ahead.
If I could.
Sure.
Yeah, I just wanted to comment to one other topic that was discussed around renewable energy and biogas. That's definitely an area of interest across the industry, and the challenge there is cost effectiveness, and so large wastewater plants definitely have the ability to deploy it, put in anaerobic digesters and the gas recovery systems and energy conversion systems, whether it's CHP or converting for pipeline use, natural gas. But then there's the challenge. Many of the majority of wastewater plants are small, and so the challenge is going to continue to be, will technology improve to make that more cost effective at a smaller scale?
Thank you. We've got about 10 more minutes. I haven't seen any questions from the audience, but I'm going to ask in the time that we have left, if Vince, you and Peter and Katie, if you have any additional thoughts on this subject, beginning with you, Vince.
I do not. I think Katie and Peter both, talked about some other dimensions, and we discussed, a few of Katie's questions. So I'm not sure that I have anything to add at this point, but happy to answer any questions that might come in.
Katie, maybe from a policy perspective, how would you answer some of the challenges we have here? For example, is when water companies use the water supply to open, this is a policy question, I guess, to open a bottling plant, water bottling plant. And I guess I'm going to ask both you and Peter. Peter's kind of in the business, and how would you react to that? I mean, one of the things is that, and we have the whole water as a public trust issue here. We're grappling with that legislatively right now. But how would you answer that question, or your observation of how we sell water through the tap, but how do you feel about selling water via a water bottling plant?
Well, it's certainly not very efficient from the energy.
Well, the plastic is one thing, and that's right.
Yeah, but I think this actually highlights a kind of a bigger kind of problem, which there's a very kind of inconsistent valuation of source water. So many utilities, I believe, they'll have a surface water source, which in their list of assets doesn't actually have a value assigned to it. It's kind of taken for granted. The same way we don't assign a value to the wind, even though we depend on wind for renewable energy. And I think there's a sort of underlying issue that we don't really have at the moment a good sense of the value of water services, and so this makes it difficult to sort of create an ordering, if you like, of what's the most valuable service, and when supplies become scarce or more difficult to procure, what services are the highest value and need to be preserved. And I think people have a general intuitive sense that, given the importance of clean water to basic health, that's a very high value, even though it's not a high price. So I think there's from my perspective of looking at how we use those valuations, say in energy policy, I feel like that's kind of missing on the water side, and it's not necessarily going to translate to assigning prices to these things, but I think it should be kind of clearer, like what the value of these services that people have currently access to, how important it would be to try to preserve those relative to one another.
Thank you. That's very good comments. And Peter, you're in the business of selling water, and certainly we as regulators want regulated water companies to sell water, but how do you respond to that? The fact that some people say, the water is a public trust, and really we have to be more cautious in terms of selling it through a commercial operation.
Well, yeah, I think we, think of ourselves as stewards of the resource. I think everybody, whether you're a private water utility or a public entity, I think generally that's the attitude, and I think the question to a bottling plant, I completely agree with Katie, and I think we all agree that is a very inefficient way of delivering this necessary resource, and so I won't judge the companies that do that, but as a public water utility, publicly owned water investor-owned water utility, but serving water to the public. Our goal is not to sell as much water as possible to make as much profit as possible. It's to have a sustainable industry, to be certainly make a profit in the process, but it's to be sustainable, to be affordable to the customers, and to deliver that essential service. I agree with Katie. I mean, I really like the way she described it, that we take for granted the critical value that water has in our lives, and the American Water Works Association for the last several years has had somewhat of a campaign on the value of water, trying to help increase public awareness of how important it is. Again, not from the profit-making side of it, because that's really not what it's about. It's about delivering essential service for public health, and that's what we're in the business of doing.
As we've heard it, for those of us that have been in this business for some time, it's the only utility that we ingest. We can't live without it. We can't put fires out. We can't do economic development. We can't do irrigation or agriculture. So it's something, and Katie's right in terms of, the cost of water, and it's still a utility that we need, and it's relatively reasonable. So any final thoughts from anybody? We're getting towards the end of the webinar here. I think this has been a tremendous topic, and really something that we need to continue to keep at the forefront in the regulatory world and in policy, as we talk about energy, water policy around the country. And as I said, we're in the process now of having our water supply plan, our water plan, be adopted by the Connecticut State Legislature in the spring, and we're very, very happy about that. And about 20 states have water plans at this point in time. So, any final thoughts?
I'd just like to mention that one of the in the research world, we've been trying to get DOE more interested in water, all aspects of it. And I just wanted to mention that if any of these issues are important to utility regulators, that you can really help raise the profile of these issues with DOE, and that would help get more resources directed towards these research problems.
Katie, thank you. Kate, and I appreciate that. And we do, as National Association of Regulatory Commissioners, we work very closely with, of course, the Federal Energy Regulatory Commission and with Department of Energy as well. But we should take actually the results of the 4 webinars that we had regarding water and energy, and talk to some of our friends over there to continue to heighten the awareness and education of this subject. So with that, if there's no further comment, I'd like to very much thank our panelists really for, I believe, was a very stimulating discussion. This afternoon we could go on and talk a lot more. Vince Tidwell from the Sandia National Laboratories, who's been our partner with this seminar, Peter Keegan, who is with American Water, and Katie Coughlin from the Lawrence Berkeley National Laboratory. Thank you so much, and wishing everybody a happy and healthy holiday season. Thank you.
Thanks, Jack.